Hello, this is our second video for our section about log-log graph paper. In our first video, we saw this example, given some data, had Excel find the power trend line, and it did pretty good. Nice R-squared value of 0.99 and a reasonably good fit. And the sum of the squared error, which is what we're really trying to minimize, was a little less than 2,000. But I claim with log-log graph paper, we can actually do better than Excel. So let's take a look. So here's our log-log graph paper, and notice I've got 3 cycles on each axis because that's all I'm going to need for this particular data set. But let's go ahead and make sure we have the right scale. So since our x values start at 4, I'm going to start this at 1 and then go up to 10, 100, and 1,000. And since our largest x value is 879, then all of my x values should fit on this axis. On the y side, I could potentially start at 10, but one thing we'll see in a minute is that when you find the y-intercept, it's nice to be able to actually read it right off the line, right off the one axis. And 13 would be pretty close to this corner, and I would rather have a little more space just in case the line is steep. Now this may or may not work, but I'm going to make this a 1, 10, 100, and then up here is 1,000. Now, once again, all my data fits within that scale, and it's possible that starting at 0.1 would be a better choice, but until we try it, we won't know for sure. But let's start with this for now. So our first data point is 4, 13. So, of course, 4 is right here. And then 13, remember, since this is 10, then this is 20. And since we have 1, 2, 3 tick marks, then 13 is going to be probably around there somewhere. So 4, 13, we'll say is about there. 17, 23, by the same reasoning, 17 is going to be about there. And 23 is going to be somewhere in there. It's about there. You don't have to be perfect, but the more accurate you are on plotting the points, the easier it will be to get a good line here in a minute. 93 is going to be real close to 100, and of course 60 is right on the line. It's about there. 153 is going to be real close to the midpoint between 100 and 200, and 90 is here, so about there. 567, there's no more individual lines, so we'll just have to estimate about there. Up to 238. So 238, this is 200, so 238 is probably in there somewhere. I'm going to say it's about there. And finally, 879 is going to be about there. And 319, we'll say it's there. Sometimes it's hard to see all these lines and get a great feel for where all the dots should be, but take your time and you'll be able to get used to the logarithmic paper after a while. So what do we notice? I see that the plot is pretty linear. It's not perfectly linear, so a power model is not going to be a perfect fit, but it's close enough to be worth a try. So we want to fit a best fit line, and here's where we can do better than Excel. Is we know that not all points are created equally in terms of minimizing the sum of the squared error. And the reason for that is if this was regular graph paper, an error, say, of an inch here versus an error of an inch here would be equal. It'd be whatever the scale of the y-axis is in terms of inches. But notice an inch here is about 6 units. Well, 6 units down in this part of the graph paper is just 6 units. But 6 units up here, because we're in the hundreds, is actually going to be 600. So if I'm off an inch here, I'm only off 6. If I'm off an inch here, I'm off 600. Obviously, I want to be off less, as small as an amount as possible, and so I need to prioritize these points over these points. So when I draw the best fit line, I want to make sure I go through these data points a lot more closely than the other ones. So in particular, I'm going to draw something maybe like this. Now you can draw your own line, see what you come up with. It may not be exactly like mine because there's no guarantee that this is the best choice, but at least it's in the ballpark because notice I've hit these last points where the Y values are worth the most pretty accurately. And even though I have a lot of error here, again, I know that that's not going to be that much compared to up here. So now we need to calculate our model, the parameters A and B. So we know the formula is y equals a times x to the b, but how do we calculate a and b? Remember, b was the slope of our transform equation. Now we can't calculate slope in the usual way because the values here are transformed. So what I need to do is either calculate it through measurement. I could actually draw a triangle, and that rise over run, if I chose to measure that, that would give me my slope. But another way is to use some trigonometry and just find that angle. And if we can find that angle, then we know the tangent of that angle is going to be that ratio, rise over run, which is going to be the b value or the slope that we are interested in. So what we really need is alpha. And for that, we need a protractor. So grab a protractor, try to line up with a point as best you can. And I'm getting somewhere between 35 and 36 degrees. It's a little hard to tell, so let's split the difference. So we'll say this is about 35.5 degrees. So now I need to calculate the tangent of that. And the tangent of 35.5 degrees turns out to be about 0.713. Now, we probably don't need that many decimal places, but we'll try it out, and then if we need to adjust here in a minute, we can. Okay, what else? So that gives us the B, and so now we need to calculate the A. Well, remember, in our transformed model equation, it was log of A. Well, since it's log of A, I can read that directly off of the axis. And log of A is right here. And since that's between 2 and 3, then it looks like that is 2.5. So if B is approximately 0.713, then A is approximately 2.5. And so our model then is 2.5 times x to the 0.713. Now that's just an estimate based on our best fit line. We'll try it out on Excel and see how good we did here in a second. So we're back to our spreadsheet, and I left a spot for A and B because I want to allow myself to change those if I need to. So for now, A is 2.5 and B is 0.713. And remember, our model was just the A value. So F11 times the X value, which is A2, raised to the B, which is F12. And we get 6.7. And it's nice to be able to check that against our original model and see how close is that to the line we drew. And I look and I see that 6.7 is not too far off. So we may have a little error, but we'll see after we drag this down. But before I drag it down, remember I want the A and the B to be fixed. So I need to make these absolute cell references. So I need to freeze the 11 and the 12 with dollar signs. And then if I drag that down, I get some values. Notice the good news is these last 4 data points are really close to the numbers I have here, which indicates that my parameters that I calculated are a pretty good fit for what I actually drew. So let's try this squared error. So the model minus the actual squared. Drag that down. And then the sum to get the sum of the squared error. And notice with the log paper, we did significantly better, an order of magnitude better. We went from almost 2,000 to less than 200. And there's no guarantee that this is the best. We might be able to do even better, but we definitely have already seen significant improvement. So if I want to, I can actually see a scatter plot of this. And to make sure that I'm actually not confusing them, I'm going to change the chart type for the log-log model to be a line. And so the nice thing here is that I can see my curve, and I can see that this does look pretty close to the line I drew on my paper. It might be a little bit low. So, and if I go back to that 35.5 degrees, maybe that was a little bit of an underestimate. So I might kick this up to say a 0.72 just to see what that does. That's a little bit high, so maybe I can lower this down to 0.717, split the difference. And notice that actually does pretty good. Now my sum of the squared errors is less than 100. Now one challenge is there's no guarantee that 2.5 is the right A value either. So it might be that if I raise or lower this, I can do a little better. If I take this down to 2.4, well, that's worse. 2.6 is worse. So for our purposes, this seems like a pretty good fit. So I would stop here. But keep in mind, because of the nature of having two parameters that need to change simultaneously, just because I zone in on one of the parameters doesn't mean that a completely different value might not still be better if I adapt the A accordingly. And we could play around with that more carefully if we wanted to. But since this is such a great fit, especially in terms of SSE, we'll stop there. So that's it for this section. We'll talk about semi-log paper in the next video. We'll see you there.